So, in the last lecture we have been discussing about multidimensional mapping of data spaces, like how to choose maybe suitable ways to map high dimensional data in terms of the kernels, like how to choose a suitable access expression for the different data segments. So, those were just some initial thoughts we discussed, and we saw that what is advantageous in which case, and of course, this would be more clear in future when we discuss more examples and provide more assignments with respect to different kind of handling different kind of high dimensional data spaces and creating what we call as access expressions. That means how does a thread really identify what is the memory element it is going to work on. And just to recap, that this was based on a thread's knowledge of its block ID, thread ID variables, and it's being able to use those variables to create suitable access expressions for the different data points it was going to work on. And as we saw that it's very much a function of how do you define the grid and the block. That means whether you define a 2D block or a 3D block and a 2D grid or 3D grid, and accordingly your access expressions are subject to change. So, this is something you can try with more examples, and we will also try to show that with examples in terms of assignments that run. Now, we will move on to another important topic of synchronization among threads. Now, first of all, what is synchronization? In general, with respect to parallel programming semantics, synchronization would essentially mean some points in the program where we definitely know that okay, this is a point where the threads have computed up to this point, and once this point of computation is reached, this is where every thread should reach, and together, or if some thread reaches this point faster and then some other thread reaches this point, then the thread which reaches this point faster should wait for the other threads to come up to this point, and then again they can go forward. So, it is basically a primitive through. So that is why we call it a synchronization point, because that is where every thread should stop. Maybe they can collaborate together, they can ensure some sanctity of reads and writes on the data variables, and then they can move forward with further computation. So, we will see that, I mean, of course, again this is a high level idea which can only be clarified through some major examples that we will touch upon. So, let us try and understand how synchronization can really be enforced on different threads which are computing in a CUDA program. So, as we know that the kernel launches a grid of threads, the grid contains a set of blocks, and these blocks contain threads packed internally, and these blocks are actually getting scheduled inside the SMs, right. Now, each block can execute in any order relative to other blocks. Now, this is a very important thing. So, if you take an example that suppose you have got a device and you have got two devices in your system, two SMs, right, and maybe in SM1 you have got the blocks 0, 2, 4, 6 scheduled, in SM2 you have blocks 1, 3, 5, 7 scheduled. So, overall your kernel has launched this many 0 to 8 block ID blocks, right. If you have two devices, there can be a possible way in which these devices are processing the blocks. Of course, this is not a unique way, there can be other ways. Like for example, suppose I have 4 devices, I can have a mapping where block 0 and block 4 are mapped to device 0, device means the SMs, and like that. So, there can be various possible mappings of blocks into the SMs. Each block can execute in any order relative to other blocks. That means, once I have launched all the threads in a grid, there is no relative specific execution order, like which thread will execute faster with respect to some other thread. I do not have any control over that unless I put in some extra primitive. So, every block of thread can execute at its own pace. That is the point that we are trying to decide here. Essentially, the GPU has got a complex scheduling hardware. There is a 2-level scheduling hardware, and it depends very much on how the hardware is going to schedule the blocks. There is some high level knowledge available in open domain about that. However, not every detail is available till now in the open domain. It is very much part of the implementation of the GPU, but what is known in open domain is that there is a 2-level scheduler. So, At some level is decided which blocks are going to be part of which SM, and inside the SMs we have schedulers to decide how to execute the blocks. We will get into more details later on, but for the time being let us understand that as a programmer you do not have any control over which blocks executes in which order. You have launched the kernel that would initiate all those set of blocks, that will initiate this entire grid. Then it is part of the hardware's the architecture's hardware scheduler's job to execute them in any order. However, certain notions, certain scheduling notions get enforced, which we will discuss. So, the important takeaway from this slide is that blocks can execute in any order relative to the other blocks, and there is a lack of synchronization constraint between blocks. This is a good thing because it enables scalability. So, as a programmer you cannot enforce synchronization across blocks of code. That means, I cannot enforce that block 0 will execute only, let us say, after block 5 executes, or similarly block 6 executes only after block 1 executes. I cannot enforce that. This actually is considered a good thing with respect to the hardware, because since this cannot be enforced unless you do some fancy programming. Again I would repeat, if you write a normal vanilla CUDA program, you cannot enforce such a thing, and so the hardware is at full freedom to execute the blocks depend on the amount of SM that is, or SPs that are available, that are free, and it can schedule them with full freedom and actually provide the maximum throughput that is possible. That is the good thing about not synchronizing across blocks. However, since that is a question, it is of course understood that synchronization can be done among threads inside a thread block. That is the very point we are trying to roll in here. So, when you launch, so I will just repeat, this is very important. When I am launching the kernel, all these blocks are getting, thread blocks are getting launched. They will be mapped to the individual SMs, and inside the SMs the order in which the blocks execute, or across SMs the order in which blocks execute is beyond the programmer's control. So, I cannot really enforce a synchronization constraint among the blocks. However, as a programmer what I can do is I can enforce synchronization constraints on threads inside a thread block. So, inside a thread block the threads may cooperate with each other and share data with help of local memory. More on this we will see later on. First of all, let us understand how synchronization among threads can be enforced. So, for that you have the CUDA constraint sync threads, which is used for enforcing synchronization. Okay, let us see some examples on that. For example, let us take this sample computation here. Your input is an 11 cross 11 matrix, and you want to output a vector of size 12, where each element represents the column sums and the last element represents the sum of all the column sums. So, you want the thread here to compute, I mean it should not compute anything, it just reports the value for column 0 here. Thread with ID 1 would do a partial sum of thread of this position and the next position. Basically the position, the entries in M, I would call them M01 and M00 M01, and this is M11, the sum of these two locations, that it should compute and put in here. Thread with ID 2 should compute this sum and put in here, and like that, and finally somebody should be actually computing the sum of this entire array and putting it to this location, right. So, this is what we want to do. So, now we need to understand that why synchronization would be necessary here. Synchronization would be necessary because we want all the threads to execute the same kernel code. However, the amount of partial sum computation that each thread is going to do is different, right. Because if I pick up this thread, the one I am marking here, if I pick up this thread, I want it to sum only up to this point, right. So, as you can see that although these threads are launched with different IDs, the amount of work you want the kernel to make them do is different. That would also mean each of the threads are going to finish their execution at different points of time, right. Now, if these threads are going to be inside a single thread block, which is the case here, then I need to make the thread which computes its job earlier, I need to make it wait for the other threads which are going to complete their job later on, right. Why is that so? Because unless all these intermediate values are ready, I cannot ask some thread to do a summation of all the entries here, right. Because I want this thread to compute the partial sum of these points and put in here. I want this thread to compute the sum only up to this point and then put it here like that, and only when this is done, then I can go and do the computation of a summation of all these values and put it here, right. Which means I need to split this computation across different phases. In phase 1, all these partial sum computations should be done and these results should be updated. Only after that I should like to have a sync, so that I have to enforce. So, for that I would like to put this sync thread here. Only after the phase 1 is completed for all the participating threads should some thread go on and work with these values. So, if I do not do a sync thread here, something random can happen, we will see that. So, for example, let us look at the code. So, this is the host side program for synchronization. So, you have two CUDA main copy commands using which, so essentially you are transferring you are transferring from the host to the device the 2D array M and the 1D array AV, which is going to be your result, and from the DIM3 primitives that you can see for grid and block, you are just launching a single block, and that block is also, you are launching a single block because as you can see these entries are all 1 in the grid declaration, and in the block declaration you can see that you are just launching these 11 threads, right. So, it is a one dimensional block and that is the only block that you are launching, and with these launch parameters you are launching the kernel sum triangle, and this kernel is going to work on now the device side arrays DM and DV, right. So, n is the size of the input matrix each dimension, right, and once this kernel's execution is done, you want to copy back this content of DV to the host side 1D array V, right. So, this is your simple host code here. Now, let us look at the kernel code. So, the kernel code is going to tell you what is the per thread activity, and let us have a look what is the per thread activity. So, the first thing you will do is you will consider what is the thread ID. So, in this case, since I have just a single block and that block is also a 1D block. So, I just have to care about the thread ID x.x variable, and this variable is going to give me the this variable is practically going to give me the column on which the column of the 2D array on which I am going to operate, right. So, let us pick a sample value of j. Let us say I am going to talk about the column with ID 5. So, that means I am talking about the thread with ID 5 starting from 0, right. So, now all that is going to happen is, if you look at this picture heaven, like, so I am talking about this thread. So, it is going to sum up 0, 1, 2, 3, 4, 5, these 6 values starting from 0. So, you compute the sum of the quantities here with which you access through this access expression M. I is the row number starting from 0, you go up to I less equals j. So, you go up to j minus 1, right, and so you complete that many rows and then come to the jth column. So, in that way, with this expression, if you look at this expression I times n plus j, for different values of j you are able to access these different locations, right, because fundamentally this is all sequentially located, right. So, with that kind of an access expression you are able to sum up all those elements in the column with ID j, but that is also up to the first j elements, right. That is what you are summing from the 0th through the j minus 1, that is the j elements, right. So, once this is done, you store this sum, this thread will store this sum in the location Vj of the output array. So, that means once this computation is done, it will store this at this location of the output array. Fine. And after that we have a sync thread, like we are discussing that, okay, once every thread has computed these partial sums and they have stored these results in the output array, there is a sync thread. So, that means every thread stops here. Why? Because I want to compute the summation across this array and store that sum at this point only when the job of all these different threads are completed, right. That is why I will put that sync thread after the partial sum computation and storage in V and before that summation starts occurring across V, because I want to ensure that before I do the summation across the entities of V, all the entries of V are ready, right. So, that is why after computing this Vj entry, I put the sync thread. Once all these entries are ready, then I get into to ask one of the threads that okay, now you compute the sum across the columns. So, once each thread finishes computing the sum across columns, the total sum is computed by the last thread. So, essentially how do I choose which thread is going to do this job? As you can see that we have launched these many threads, these 11 threads we have launched, and the last thread. So, as you can see we this is the per thread activity for this kernel, and only the thread with ID n minus 1 would enter into this block, right. Only the thread with ID n minus 1 will enter into this block, and then what this thread is going to do is it is summing up the entries of V and storing it into the location V n. As you can remember that V has got one more space, extra space. So, V starts from V 0 and it is up to V n. So, only the thread whose ID j would be equal to n minus 1. So, that is essentially the thread which is computing this entry, that will get into that if block. The other threads are not getting to the if block, but only that thread would do the summation and then store it up here. Now, the question is, then what was the requirement of sync thread? The requirement was there because we want the following to be ensured, that when this summation is being done on the output array, all the entries, all the Vi entries in the output array should be ready. Now, it may happen that you run the code without the sync thread, but you still get the result. Question is, there is no guarantee that you will really get the result. You may get the result, you may not get the result. Why? Because without the sync thread, then we are assuming that before the last thread starts doing this computation, everybody else has finished. It is not guaranteed. Now, the question is, when do I really not have the guarantee? Okay. If we are working with small number of threads, where the threads are all part of the warp, then I can have this guarantee. But as we have discussed that in a general setting, when I have very large number of threads in a block, I have got very large number of threads in a block, then I cannot guarantee. Only when the threads will be part of a single warp, then I know that the threads will execute in lockstep, and then I have a guarantee that okay, when the last thread is going to finish, by that time the previous threads which are in that same warp have actually finished. But in general that may not be true, because only in the case when I am having multiple warps which are created inside a block, right. So, just to highlight your example, if you are running this code with small number of threads like this, the threads will be part of a warp and you may not need this sync thread. But if you are running this code on a big thread block, which is going to launch multiple warps, then you do not really have a guarantee, because then what is going to happen is each of the warps are going to schedule threads in different ways. We will come to formalizing that later on, but just to understand, I am trying to remove a notion here that you may run this code on a small setting of a block and see that well, yes, without the sync thread still things are fine. I am just trying to say that it may or may not be fine. it depends on the size of the block, and we will see that exactly in which case it is good and which case it is bad. But in general, you need to appreciate that when I am running these threads, I do not have any guarantee that this thread is going to finish last or this thread is going to finish first. It depends on how many threads are launching. If I launch this small number of threads, well, we are taking this small number of threads just for a figure representative purpose. It may happen that I do not need the sync thread, but for a significantly large number of threads, I do not have any guarantee. So, anyway, from a programmer's point of view, I need to ensure that all these entries in the V are really ready. That means, all the threads have really done their job before this last thread goes to compute this entry, right. So, for that purpose, I will need to put this sync thread here, fine. So, that would be about this small program, and then let us look at some other variants. So, suppose I hope just to recall, I hope the idea is clear, that I just wanted to put this point across, that it may not be the case if we are using a very small number of threads or we are launching a small block, but in general for a significantly large block, and in general unless I put this sync thread here, I am just trying to summarize here, I do not put this sync thread here, then there is no guarantee on how fast each of the threads should compute. So, to enforce the constraint from the programmer's point of view, I would like to have the sync thread here, fine. So, looking at other variants of the program. So, now let us consider the situation that we only sum up the elements at the odd indices. So, that would mean if I look at the example, so I am just summing up the elements at these indices here. So, at index 0, the 0th row element, the 3rd row element, I am not including the elements at the row number 0 or row number 2 like that, right. So, again I am including first row element, first row and 3rd row is included here, first row and 3rd row is included here, first, 3rd and 5th row is included here, again first, 3rd, 5th and 7th row is included here. So, we are going in a one hop basis. If I am trying to do such a variant of the same computation, how would really the kernel look like? Well, it is simply a matter of putting in a choice statement here. So, essentially I have the same code. So, I believe this should be a thread ID here, just a minute, sorry for this. Yes. So, essentially it is the same code. Okay, let us just review the earlier code once again. So, this was your original code, and if you come here is basically the same, but you are doing the sum only for the odd indices. So, you push in a small check if I percentile 2. So, if that is 1, that means you get in for the odd indexed rows, and otherwise you do not get in, and only in those cases do the sum, and in that way everything remains same, right. Fine. So, the rest of the code is same, you add till your addition is still carried out by the last thread. So, it is all the same here. So, you have the same thing, the same setting, but as we are explaining that every thread is hopping over an element, and again we will need the sync thread here. If I have a significant number of threads, all of the threads are not pushed into a warp. So, you do not have any control over which thread is progressing at what speed. So, after each of their partial sum computation, again I would definitely need the sync thread here to ensure that yes, every thread has done the computation properly, I mean they are all finished, and accordingly now we will instruct once every thread reaches this point, then this is the synchronization point. Only when they reach here, they are again restarted for a fresh run, and again the last thread starts summing up these entries to compute the last entry. Now, consider a different variant of the program. Again, we are summing all indices like the first example. So, like we are not again hopping over the rows, we are going to sum all the rows, but now we are trying a modification that instead of using the last thread for the final reduction, that means for doing the final summation computation, we want to do the final summation computation in a collaborative way by using all the threads. Why? Because as we can understand, if I leave that job to one thread for a significantly large block, it may require a lot of time, but I may want to speed it up by distributing that work among all the threads, because finally why do I leave it for one thread? There are many other active threads which are simply sitting there idle, right? So, again the first part of the code is again exactly the same. For this piece of code, let us first try to understand what is the activity that each of the threads are doing, and we can this activity can be actually visualized graphically in a better way. So, if you look at this example here, so we have the thread IDs all plotted like this in the x axis, and we are showing what each of the threads are doing in each iteration, right. So, let us just follow one or two iterations and things will be very clear. So, first of all, in the first iteration of this loop, every thread is going to enter this loop with an s equal to 1. J is the thread ID. Now, as you can see in the if condition, we have j plus s less than n. So, since j is the thread ID and s is 1, so this will be satisfied by all but the last thread, right. So, this will be satisfied by all but the last thread. So, for all the IDs 0 to 10, this is fine, right, because n is 11 in our example here. But the first part of the conditions in s is 1. So, I am doing essentially a j percentile 2 equals 0. So, that is only going to be satisfied by the threads with the even indices, right. So, all the threads with the even indices is going to do something in the first iteration of the loop, and what are they going to do? They are simply going to add the entries in the array at the location Vj with Vj plus 1, right. So, essentially for thread ID 0 is going to compute V0 plus V1 and store it in V0. So, that is what we have, V0 plus V1 and store it in V0 by thread ID 0. Thread ID 1 is odd index, does not do anything. Thread ID 2 is even index, does V2 plus V3 and stores it in V2, and similarly everywhere. So, at the end of the first iteration of the loop, half of the threads have actually collaborated among each other, and they have successfully computed the partial sums at a stride of 1. S denotes the stride. So, with one hop, half of the threads have collaboratively computed the partial sums. So, we can understand how things are going to proceed here. In the next iteration of the loop, another half of the threads are going to be active, and they are going to increase the stride by double, that is s equal to 1 to s equal to 2, and they are going to do the partial sum computation of entries this and this, this and this, and this and this, right. So, essentially if we go back to the code, in the next iteration s gets multiplied by 2. So, we shift from stride of 1 to stride of 2, and the thread ID 0 will again satisfy the condition, but it will get in the loop and compute a V0 equal to V0 plus V2 here, right. So, if you look into the code, initially it did V0 equal to, so if I just look at what thread ID 0 did, so here it computed V0 plus V1, this value got stored in V0, and this is now added up with the content of V2, and then next it will get added up with the content of, in the next iteration with V4, in the next it will get added up with the content of V8, and in the process the V2 that it is getting, we already have V2 to be equal to V2 plus V3, if we look at V4, I already have V4 plus V5, and then V4 plus V5 plus actually V6 plus V7. So, in that way I have the sum up to V8 and the other elements will also come in, right. So, in this way, as you can see that the entire computation will make a progress, the entire computation makes a progress and all the threads collaboratively compute the sum. So, just to repeat, in the first iteration half of the threads are simply adding their own position with the next position. So, in that way I have half of the partial sum stored here. In the next iteration I have further half of the threads, that is 1/4 of the threads computing these locations along with the a location at a stride of double space, that is s equal to 2. In the next iteration we again have a further half of the threads which is actually summing up this location along with a stride at an even double space. So, s equal to 4. In that way I am able to compute the sum for the entire array. So, you can just write, if you are trying to prove the correctness of the program, if you can just write that the final location sum is equal to these two locations sum. This is again equal to sum of these two locations and this location is again equal to a sum of these two locations, and you can go back like this and finally you get an expression where this locations is equal to the sum of all the individual locations, right. So, that ensures the correctness of the reduction, and we can actually prove that this simple optimization gives me the correct result, but it actually engages all the half of the threads together in the computation, unlike engaging one thread to do the entire computation. Now, observe something very important here. After this first iteration, I have got all the threads to give me the value of its own locations data plus the next location, right. Unless all these individual computations are finished, none of the threads should be allowed to go to the next iteration, because then there will be inconsistency. For example, let us say thread 0 will progress to compute this plus this, but maybe thread 2 has not completed this plus this operation in the previous iteration, right. That can happen because of the situation we discussed earlier, that in the GPU I do not have a guarantee that threads are progressing together unless they are part of the same warp, right. Unless they are part of the same warp, threads are not progressing together. Even if they are part of the same warp, based on conditional execution, the warps may diverge, and there will be other things that we have to discuss. That for the time being we can just assume that threads executing inside a block are progressing at their own speed, since we do not have a control over their execution speed because of the hardware scheduling taking care of that. I cannot really guarantee that two threads doing this partial sum computation are progressing at the same speed, but we can see that we have a requirement here. Unless each of the threads are able to do their computation for some specific value of the stride, none of the threads should be allowed to go to the next level of computation for the next value of the stride. I cannot let S progress and all the threads progress to the next iteration of the loop unless all the threads complete the previous iteration of the loop. And the way to do that is very simple. Just put a sync thread inside this loop here. So, once every thread is guaranteed to execute one iteration of the loop, only then all the threads together go for the next iteration of the loop. So, I will just repeat, once every thread is guaranteed to compute executing one iteration of the loop, only then we should let all the threads together progress to the next iteration of the loop, and this is how things should keep on going and the computation would keep on progressing, and finally we have all the threads computing together and giving me the final result. So, with this we would like to sum up our explanations on synchronization. Of course, we will have some more examples in future which will involve synchronization, but this is just to give you a basic introduction of how to and where to put sync thread primitives in the code. So, basically you have to understand at what are the points in your kernel where you need to guarantee that all the threads of thread block have actually done their computation before proceeding to the next line of computation. If there are such algorithmic issues where all the threads are going to use results computed by each other at some point of computation, or from starting from that point of computation, there has to be a sync thread statement for synchronizing the threads inside the thread block. So, just to summarize, threads inside a thread block can synchronize. You have to use a sync thread primitive, but the reason you have to use it just to be sure is that you don't have any guarantee at what speed the blocks and the threads inside the blocks are progressing inside the GPU. How is the scheduling done? We will investigate more into this from the next lecture. Thank you.